You think you understand dimensions? You don't. Most people don't. And that's not your fault. Your brain was never designed to think about this properly. But here's the thing. Richard Feynman, one of the greatest physicists who ever lived, figured out how to make dimensions click. Not with fancy math, not with abstract nonsense, with simple, brutal clarity. And once you see it his way, you can never unsee it. So let me show you what he showed us. Let me show you why everything you think you know about dimensions is incomplete, and why the truth is so much stranger and more beautiful than you ever imagined. Let's start with something you think is obvious. A point has 0 dimensions, a line has 1 dimension, a square has 2 dimensions, a cube has 3 dimensions. Simple, right? You learned this in school. You've known it forever. But here's what they didn't tell you. Here's what Feynman understood that most people miss. Dimensions aren't just counting directions. Dimensions are about freedom, about how many independent ways you can move, about the fundamental structure of reality itself. Let me explain what I mean. Imagine you're a prisoner. You're locked in a cell. But this isn't a normal cell. This cell is so small that you can't move at all. You can't go forward, backward, left, right, up, or down. You're frozen in space, completely stuck. How many dimensions of freedom do you have? 0. You're a point. You exist, but you cannot move in any direction. That's 0 dimensions. Not the absence of space, but the absence of freedom to move through space. Now the prison guard loosens your chains slightly. You can move, but only along a wire. You can slide forward or backward along this one wire, but that's it. No left, no right, no up, no down. Just forward and backward. How many dimensions of freedom do you have now? 1. You live in a one-dimensional world. Your entire universe is a line. Everything that exists somewhere along this line. And here's the crucial part. From your perspective, inside this one-dimensional world, you cannot even imagine what left or right would mean. Those concepts don't exist for you. The guard loosens your chains again. Now you can move forward and backward, but also left and right. You're on a flat surface. You can slide anywhere on this plane, but you still can't go up or down. 2 dimensions, 2 independent directions of freedom. This is the world of the bug we talked about before, the bug on the surface of the sphere. 2 dimensions of movement, but nothing else. Finally, the guard removes all the chains. You can move forward, backward, left, right, up, and down. 3 dimensions, 3 independent directions. This is the world you live in, the world you know, the world that feels complete. But here's Feynman's question, the question that changes everything. Why should it stop at 3? Think about it carefully. What makes 3 special? What makes 3 the final number? You can move forward and backward. That's 1 dimension. You can move left and right. That's a 2nd dimension, independent of the first. You can move up and down. That's a 3rd dimension, independent of the other 2. But why can't there be a 4th direction? A direction that's somehow perpendicular to all 3 of the ones you know. Not up, not down, not left, not right, not forward, not backward, but something else entirely. Some other direction that you simply can't perceive. Now, your brain immediately rebels against this. Your brain says, that's impossible. I can see all of space. There's nowhere else to go. Up, down, left, right, forward, backward. That's everything. But is it? Feynman would ask you to consider the bug again. The bug on the 2-dimensional surface. That bug would say exactly the same thing. I can see all of space. Forward, backward, left, right. That's everything. There's nowhere else to go. And the bug would be wrong. Dead wrong. Because up and down exist. The bug just can't perceive them. So here's the terrifying possibility. You might be the bug. You might be living in a higher dimensional space, moving through it, existing in it, but completely unable to perceive the extra dimensions. You might be like a prisoner who's only aware of forward and backward, completely oblivious to left and right, even though left and right are right there, real, physical, surrounding you. This isn't science fiction. This is a genuine possibility that physicists take seriously. Now, let me show you why this matters, why Feynman cared about this, why understanding dimensions isn't just an abstract game. It's about understanding the fundamental structure of reality. And it starts with a simple observation. The laws of physics look different in different numbers of dimensions, not just mathematically different, actually fundamentally different. Things that are possible in 3 dimensions are impossible in 2 dimensions. Things that are possible in 4 dimensions are impossible in 3 dimensions. The number of dimensions determines what can happen, what can exist, what laws govern reality. Here's an example Feynman loved. In 3 dimensions, you can tie a knot. You can take a rope, loop it around, thread it through itself, and tie a knot that stays tied. Try to do that in 2 dimensions. Try to tie a knot on a flat surface where the rope can't leave the surface. You can't. It's impossible. The rope always crosses itself and you can slide the loops apart. Knots don't exist in 2 dimensions. The topology is different. The structure of space itself doesn't allow it. Here's another one. In 3 dimensions, you can have stable orbits, planets orbit stars, moons orbit planets. Electrons orbit nuclei, sort of. These orbits are stable because of an inverse square law. Gravity and electric force both follow inverse square laws in 3 dimensions. The force gets weaker as 1 over distance squared. But in 4 dimensions, the force would follow an inverse cube law, 1 over distance cubed. And with an inverse cube law, orbits aren't stable. Planets would spiral into stars or fly away. Atoms wouldn't hold together. Chemistry wouldn't work. Life, as we know it, couldn't exist. This is profound. The number of dimensions doesn't just change the math, it changes everything. It determines what structures can form, what patterns can emerge, what complexity is possible. 3 dimensions isn't arbitrary. It's special. It allows knots and stable orbits and all the intricate structures that make the universe interesting. Fewer dimensions would be too simple. More dimensions would be too chaotic. 3 is, in some sense, just right. But that raises a question. If 3 is special, why do physicists talk about extra dimensions? Why do theories of physics propose 4 spatial dimensions, or 5, or 6, or even 10 or 11? Here's where it gets interesting. Feynman understood something crucial. There's a difference between large dimensions and small dimensions. The 3 dimensions you know, up, down, left, right, forward, backward, these are large, infinite, or at least vast. You can move as far as you want in these directions and keep going. But a dimension doesn't have to be large. A dimension could be small, very small. So small that you'd never notice it. Imagine this. Imagine that space has a 4th dimension, but that 4th dimension is curled up, wrapped around in a tiny circle. So tiny that you can't see it. You exist in this 4th dimension. You're extended into it. But the extension is microscopic. Smaller than an atom. Smaller than anything you could ever measure. From your perspective, the 4th dimension doesn't exist. But mathematically, it's there, and it has consequences. Feynman explained this with one of his famous analogies. Imagine an ant walking on a tightrope. From far away, the tightrope looks one-dimensional. It's just a line. The ant can only move forward or backward along the rope. But zoom in, look closely at the rope. The rope has thickness. It's actually a cylinder. And the ant, if it's small enough, can move around the rope. It can walk forward and backward along the length, and it can also walk around the circumference. 2 dimensions, not 1. But the 2nd dimension is curled up. It's finite. It loops back on itself. And if you're looking from far away, you don't even notice it. Our universe might be like that tightrope. We think we live in 3 dimensions, but there might be extra dimensions, curled up so small that we can't detect them. We move through these dimensions constantly, but the movement is confined to such a tiny scale that it's invisible. And yet these hidden dimensions might be crucial. They might explain things we don't understand. They might be the key to unifying all the forces of nature. Now here's where Feynman's genius really shines. He didn't just talk about dimensions abstractly. He showed how to think about them, how to visualize them, how to make them concrete, and his method is brilliant. Here's what he'd tell you. If you want to understand 4 dimensions, don't try to visualize a 4-dimensional object all at once. You can't. Your brain isn't built for it. Instead, look at slices. Look at 3-dimensional slices of a 4-dimensional object, and watch how those slices change. Let me show you what I mean. Start with something simple. A 0-dimensional object, a point. If you slice a point, you get nothing or you get the point. That's it. Now, a 1-dimensional object, a line segment. If you slice a line segment perpendicular to its length, each slice is a point, and as you move the slicing plane along the line, the point appears, exists, and then disappears. The point is the 1-dimensional object's intersection with the 0-dimensional slicing space. Now, a 2-dimensional object, a circle. Slice a circle with a 1-dimensional line. Depending on where you slice, you might get nothing, you might get a point where the line just touches the edge, or you might get a line segment where the line cuts through. And as you move your slicing line across the circle, the line segment appears, grows, reaches maximum length at the center, shrinks, and disappears. You can reconstruct the whole circle just by watching how the slices change. Are you starting to see the pattern? Good, because now comes the leap. A 3-dimensional object, a sphere. Slice a sphere with a 2-dimensional plane. Each slice is a circle, and as you move the slicing plane through the sphere, the circle appears, grows, reaches maximum size at the equator, shrinks, and disappears. You can reconstruct the entire 3-dimensional sphere just by watching the sequence of 2-dimensional circles. This is how we understand CT scans and MRI scans. We're looking at 2-dimensional slices of a 3-dimensional body. Now the jump to 4 dimensions. A 4-dimensional sphere, called a hypersphere. If you slice a hypersphere with a 3-dimensional space, each slice is a 3-dimensional sphere. And as you move your slicing space through the hypersphere, the 3-dimensional sphere appears, grows, reaches maximum size, shrinks, and disappears. You can't visualize the whole hypersphere at once, but you can visualize the sequence of 3-dimensional spheres. And that sequence is the hypersphere. That's what it means to exist in 4 dimensions. Feynman would push this further. He'd ask, what does a 4-dimensional cube look like? You can't see it all at once, but you can see its 3-dimensional slices. Start by slicing a 4-dimensional cube, called a tesseract or hypercube. At first you get nothing. Then, suddenly, a 3-dimensional cube appears. It grows. At the middle of the tesseract, you get a cube. Then the cube starts shrinking, and finally it disappears. The tesseract is the collection of all these cubes stacked in the 4th dimension. But here's where it gets wild. Feynman realized that you can actually see hints of 4-dimensional geometry in 3-dimensional shadows. Just like a 3-dimensional object casts a 2-dimensional shadow, a 4-dimensional object would cast a 3-dimensional shadow. And mathematicians have computed what these shadows look like. The shadow of a tesseract is a cube within a cube, with the corners connected. It looks impossible, because you're trying to represent 4-dimensional structure in 3 dimensions, and things overlap and intersect in ways that seem wrong. But that's exactly the point. The wrongness is the signature of the extra dimension. Now let's talk about something Feynman was obsessed with, the way dimensions affect physics. I mentioned earlier that the laws change in different dimensions. Let me be more specific. In 1 dimension, things are simple. Very simple. Particles can only move in a line. They can't go around each other. If 2 particles meet, they bounce back. That's it. No complexity, no interesting dynamics. In 2 dimensions, things get more interesting. Particles can move around each other. You can have rotation, circulation, vortices. But you still can't have knots. You can't have certain kinds of field lines. The electromagnetic field behaves differently. Gauss's law works differently. Gravity follows a different force law. In 2 dimensions, gravity doesn't follow inverse square. It follows inverse first power. Force decreases linearly with distance, not quadratically. In 3 dimensions, we get inverse square laws. Both gravity and electromagnetism follow inverse square laws. Why? Because of geometry. Because in 3 dimensions, the surface area of a sphere grows as the square of its radius. The field spreads out over that surface, so the field strength decreases as 1 over the square of the distance. This is geometric. This is forced by the structure of 3-dimensional space itself. In 4 spatial dimensions, you'd have inverse cube laws. The surface of a 4-dimensional sphere grows as the cube of its radius. Forces would weaken faster with distance. And as I said, orbits wouldn't be stable. Atoms wouldn't work. Stars wouldn't work. Nothing would work the way it does in our universe. Feynman found this fascinating. The fact that physics is so intimately tied to geometry. That the number of dimensions determines the laws. That you can't separate the physics from the dimensionality of space. And this leads to one of his deepest insights. When you're doing physics, you're not just calculating forces and trajectories. You're exploring the geometry of reality. You're figuring out the shape of the space you live in. Here's something Feynman loved to point out. We don't actually know that space has exactly 3 dimensions. We observe 3 large dimensions, sure, but there could be more. Small dimensions, curled up, hidden. How would we detect them? Well, if there are extra dimensions, even tiny ones, particles can move in them. And that movement would show up as extra energy. Energy we can't explain with just 3 dimensions. Think about it this way. If there's a small extra dimension, a dimension curled up into a circle, a particle can move around that circle. And because the dimension is small, the particle's wavelength has to fit into that small space. Quantum mechanics tells us that a confined particle has energy. The smaller the confinement, the higher the energy. So particles moving in extra dimensions would have extra energy states. And we could detect those states in particle colliders. We could smash particles together at high energies and look for signs of extra dimensions. This is not speculation. This is real physics. Experiments at the Large Hadron Collider have looked for evidence of extra dimensions. So far, they haven't found any. But the search continues, because if extra dimensions exist, they would revolutionize our understanding of the universe. They would explain mysteries we can't currently solve. For example, gravity. Gravity is weirdly weak compared to the other forces. Electromagnetism is vastly stronger than gravity. Why? One possibility is that gravity leaks into extra dimensions. While electromagnetism is confined to our 3 dimensions, gravity spreads out into extra dimensions, diluting its strength. If this is true, then on very small scales, in the extra dimensions, gravity might be much stronger than we think, and we could detect this with precise enough experiments. Another example is the hierarchy problem. The fundamental particles have masses that span an enormous range. The Higgs boson is much heavier than an electron. Why? The math suggests the Higgs should be much, much heavier than it is, unless something cancels out the extra mass. Extra dimensions could provide that cancellation. They could explain why particles have the masses they do. Now, watch this. Feynman understood that dimensions aren't just a mathematical curiosity. Dimensions have real physical consequences. And one of the most profound consequences is this. The dimensionality of space determines what information you can store, how much complexity you can pack into a region, how much structure can exist. Think about it. In 0 dimensions, in a point, you can store essentially 1 bit of information. The point exists or it doesn't. In 1 dimension, along a line, you can store a sequence of bits. The amount of information grows linearly with the length of the line. In 2 dimensions, on a surface, the information grows with the area. You can pack many more bits into a 2-dimensional region than into a 1-dimensional line of the same size. In 3 dimensions, information grows with volume. Even more storage. But here's the weird part. In our universe, there's a limit to how much information you can store in a region. And that limit is determined by the surface area, not the volume. This is called the holographic principle. It suggests that our 3-dimensional universe might actually be encoded on a 2-dimensional surface, that the 3rd dimension might be, in some sense, an illusion. A hologram. Feynman didn't live to see this principle fully developed, but he would have loved it, because it's exactly the kind of deep connection between dimensions, information, and reality that he spent his life exploring. Let me give you another one of Feynman's insights. He understood that dimensions affect how things scale, how structures change when you make them bigger or smaller. This is called dimensional analysis, and it's one of the most powerful tools in physics. Here's how it works. Suppose you want to build a bridge. You build a small model and it holds up fine. Now you scale it up. You make it 10 times bigger in every direction, 10 times longer, 10 times wider, 10 times taller. What happens? Well, the volume of the bridge scales as the cube of the size. If you make it 10 times bigger, the volume goes up by a factor of 10 cubed, which is 1,000. The mass goes up by a factor of 1,000. But the strength of the bridge depends on the cross-sectional area of its supports, and area scales as the square of the size. If you make it 10 times bigger, the area goes up by a factor of 10 squared, which is 100. So the mass goes up by a factor of 1,000, but the strength only goes up by a factor of 100. The bridge is 10 times weaker, relative to its weight, than the small model was. This is why you can't just scale up a design and expect it to work. This is why giant creatures can't exist, why a giant ant would collapse under its own weight. The strength of bones and muscles scales with cross-sectional area, which goes as length squared, but the weight scales with volume, which goes as length cubed. Make an ant 10 times bigger, its weight goes up 1,000 times, but its strength only goes up 100 times. The ant collapses. Feynman loved this kind of reasoning, because it's pure geometry, pure dimensional analysis. You don't need to know the details of the ant's biology. You just need to know how things scale in 3 dimensions. And that tells you what's possible and what's not. Now here's where Feynman takes it further. He asks, what if space had more than 3 dimensions? How would scaling work then? In 4 spatial dimensions, volume would scale as length to the 4th power. Surface area would scale as length cubed. Strength would scale even more slowly compared to weight. Structures would be even more fragile. It would be even harder to build large, stable objects. This is another reason why 3 dimensions might be special. It's a sweet spot where you can have structures that are both complex and stable. Let me tell you about one of Feynman's most beautiful demonstrations. He wanted to show people how to think about dimensions in a concrete, visual way. So he invented a game where you try to visualize 4-dimensional objects by looking at their 3-dimensional cross-sections. Here's how it works. Imagine you have a 4-dimensional cube, a tesseract. You slice it with a 3-dimensional space. Depending on the angle of the slice, you get different 3-dimensional shapes. If you slice parallel to one of the faces, you get a cube. If you slice at an angle, you might get a hexagonal prism or other shapes. And as you rotate the tesseract in 4 dimensions, the shapes change. Cubes morph into other polyhedra. Faces appear and disappear. Edges connect in strange ways. Feynman would have people practice this. He'd describe the tesseract structure. 8 cubes arranged in 4 dimensions, connected at their faces. And he'd ask, if I slice here, what do I see? If I rotate this way, what changes? And slowly people would start to develop an intuition, not for seeing 4 dimensions directly, but for understanding how four-dimensional objects behave, how they project into 3 dimensions, how they change when manipulated. This is Feynman's genius. He didn't just explain dimensions, he taught people how to think about them, how to build mental models, how to connect abstract mathematics to concrete visualization. And in doing so, he made dimensions click for countless students and physicists. Now, let's address something fundamental, something that confuses people endlessly. What is a dimension, really? I've been talking about directions, about freedom to move, about independent ways to vary. But what does that mean, precisely? Feynman had a beautiful answer. A dimension is a parameter, a number that can vary independently of all other numbers. That's it. That's the definition. Think about it. To specify a point on a line, you need one number, the position along the line. That's one parameter, one dimension. To specify a point on a plane, you need 2 numbers, x and y coordinates, 2 parameters, 2 dimensions. To specify a point in space, you need 3 numbers, x, y, and z, 3 parameters, 3 dimensions. To specify a point in spacetime, you need 4 numbers, x, y, z, and time. 4 parameters, 4 dimensions. But here's the key. The parameters have to be independent. They have to vary separately. If you have 2 parameters that are related, that always change together in a fixed way, then you don't really have 2 dimensions. You have 1 dimension described in a complicated way. Here's an example. Suppose I give you 2 numbers, a and b, and I tell you they're always equal. A equals b, always. Then even though I gave you 2 numbers, you only have 1 degree of freedom. 1 parameter you can change, 1 dimension. The second number is redundant. It doesn't add information. It doesn't add freedom. This is crucial for understanding dimensions. It's not just about how many numbers you write down. It's about how many independent directions you can move, how many ways reality can vary. And Feynman understood this deeply. He knew that dimensions are about the structure of possibility, about the space of all possible configurations. Here's where this gets profound. In physics, we talk about configuration space, the space of all possible states of a system. And the dimension of configuration space is the number of independent parameters needed to specify the system's state. For a single particle in 3-dimensional space, configuration space is 3-dimensional. For 2 particles, it's 6-dimensional. 3 coordinates for each particle. For 100 particles, it's 300-dimensional. Feynman spent much of his career working in these high-dimensional spaces. In quantum mechanics, the state of a system is a point in an abstract, high-dimensional space, and the evolution of the system is a path through that space. Feynman's path integral formulation of quantum mechanics is all about summing over all possible paths in configuration space, and configuration space can have arbitrarily many dimensions, hundreds, thousands, infinitely many. This is where Feynman's understanding of dimensions became essential. He had to think about spaces with millions of dimensions, spaces that no human can visualize. And yet, he could work with them. He could derive physical predictions from them. He could make them meaningful. How? By using the principles I've been explaining. By thinking about dimensions as parameters, as degrees of freedom, as independent directions. By not trying to visualize everything at once, but instead focusing on slices, projections, and specific properties. Now let me tell you about one of Feynman's most startling ideas. An idea that connects dimensions to the fundamental nature of reality. He realized that the number of dimensions in our universe might not be an accident. It might be determined by the laws of physics themselves, or conversely, the laws of physics might be determined by the number of dimensions. Here's what I mean. In string theory, which Feynman was skeptical of but acknowledged as interesting, the fundamental objects are not particles, but tiny vibrating strings. And for the mathematics of string theory to work, for the equations to be consistent, space must have exactly 10 dimensions, not 9, not 11. 10. 6 of those dimensions are spatial dimensions we can't see, curled up small. But the theory demands 10. The consistency of the mathematics requires it. Feynman found this remarkable. The idea that you can't just choose the number of dimensions arbitrarily. That the structure of the theory constrains the dimensionality of space. This suggests something profound. That dimensions and laws are intertwined. That the geometry of space and the physics of matter are two aspects of the same underlying reality. But Feynman was also cautious. He'd remind people that just because a theory requires 10 dimensions doesn't mean space actually has 10 dimensions. It means the theory requires 10 dimensions. And if the theory is wrong, then its dimensional requirements are irrelevant. This is the scientific method. This is how you think carefully about these ideas. You distinguish between what the math says and what reality is. You test, you observe, you check. Let me give you a concrete example of how dimensions matter in real physics. One that Feynman worked on directly. In quantum field theory, particles are excitations of fields, and fields exist everywhere in space. The electromagnetic field, for instance, has a value at every point in space. That value can oscillate, and those oscillations are photons. Now here's the thing. When you calculate what happens in quantum field theory, you get infinities. You calculate the mass of an electron, and the math says it's infinite. You calculate the probability of a process, and the math says it's infinite. These infinities plagued physics for decades, until Feynman and others figured out how to deal with them through a process called renormalization. And here's where dimensions come in. The infinities in quantum field theory depend on the dimension of space. In some dimensions, the infinities are worse. In other dimensions, they're better. In exactly 4 space-time dimensions, which is what we have, 3 space plus 1 time, the infinities have a very specific structure. And that structure makes renormalization possible. The theory is renormalizable. In other dimensions, it wouldn't be. In 5 space-time dimensions, for instance, quantum electrodynamics is not renormalizable. The infinities can't be absorbed. The theory doesn't work. Feynman found this astonishing. The fact that our universe has exactly the right number of dimensions for quantum field theory to work. 4 space-time dimensions. Not 3, not 5. 4. Is this a coincidence, or is it a clue? Feynman didn't know. He'd say it's either an amazing accident or a deep principle we don't yet understand. But either way, it shows that dimensions matter. They're not just background. They're not just a stage where physics happens. They're part of the structure, part of what makes physics work. Let's talk about time, because time is a dimension too. Feynman emphasized this constantly. When we say space-time has 4 dimensions, we mean 3 spatial dimensions and 1 time dimension. Time is not just a parameter. It's a dimension in the same sense that space is a dimension. It's an independent direction. A direction you can move in, or at least a direction that varies independently of space. But time is different from space in crucial ways. You can move forward or backward in space freely. You can turn around. But time only goes one direction. You move forward through time. You can't turn around. You can't go backward, at least not in any way we understand. This asymmetry makes time special. It's a dimension, but a different kind of dimension than the spatial ones. Feynman would ask, why is time different? What makes it special? And the answer is subtle. In the mathematics of relativity, time and space are unified into space-time, but they enter the equations with opposite signs. Space contributes positively to the space-time interval. Time contributes negatively. This sign difference is what makes time different from space. It's what gives time its arrow, its directionality. But here's something wild. In quantum mechanics, Feynman discovered that you can treat time like space. In his path integral formulation, you sum over all possible paths a particle can take, not just through space, but through space-time. And in that formulation, time and space are on equal footing. You can even rotate between them, turn time into space and space into time, mathematically. And this rotation has physical consequences. It's how you calculate quantum effects. Feynman loved this, the idea that time is just another dimension, that the division between space and time is not absolute, that they're two aspects of a unified structure. And understanding this was key to unlocking quantum field theory, key to understanding how particles behave. Now here's something most people never think about. Dimensions don't have to be spatial or temporal. They can be anything. Any independent parameter is a dimension. Color, for instance, is a dimension in a certain sense. If you're describing a colored surface, you need spatial coordinates to say where you are, and you need color coordinates to say what color the surface is. The color space is its own dimension, separate from physical space. Or consider temperature. A weather map shows temperature as a function of position. Temperature is not a spatial dimension, but it varies across space. You can think of it as an extra dimension, a field defined on space. Every point in space has a temperature value. The space of all possible temperature distributions is infinite dimensional. Feynman understood this abstraction. He knew that dimensions are not limited to physical space. They're any independent variable. And this generalization is incredibly powerful. It lets you think about complex systems with many parameters as geometric objects in high-dimensional spaces. And then you can use geometric intuition to understand those systems. Let me give you one final example of Feynman's brilliance with dimensions, one of his most famous ideas. In quantum electrodynamics, you calculate the probability of a particle interaction by drawing diagrams. Feynman diagrams. Each diagram represents a possible way the interaction can happen, and you sum over all diagrams to get the total probability. Now here's the thing. Feynman diagrams are usually drawn in two dimensions. You have a horizontal axis representing space and a vertical axis representing time, and you draw lines representing particles moving through space-time. But Feynman emphasized that the diagram is not a picture of reality. It's a symbolic representation. The particles don't actually move along those lines in real space. Why? Because the lines represent paths in space-time, which is four-dimensional. And you can't draw four dimensions on paper, so you project. You collapse four dimensions down to two for visualization. And in doing so, you lose information. The diagram is schematic. It's a mnemonic, a tool for organizing the calculation. But the real physics happens in four dimensions. Feynman was adamant about this. He'd tell students, don't confuse the diagram with reality. The diagram is a map. It's not the territory. The territory is four-dimensional space-time. The map is two-dimensional paper. Use the map, but remember what it represents. This distinction is crucial, because it's easy to mistake the representation for the thing itself, to think that particles really zigzag along lines the way they do in diagrams, but they don't. They exist in four-dimensional space-time, and the diagrams are just a way to keep track of the math. All right, let's bring this all together, because we've covered a lot and I want to make sure the picture is clear. Dimensions are degrees of freedom, independent directions, ways that reality can vary. We live in a universe with three large spatial dimensions and one time dimension. But there might be extra dimensions, small and curled up, that we can't directly perceive. The number of dimensions determines the laws of physics. It affects how forces scale with distance, how structures can form, what patterns are possible. Three spatial dimensions are special. They allow inverse square laws, stable orbits, complex structures. Fewer dimensions would be too simple. More dimensions would be too chaotic. At least for large dimensions. Small extra dimensions might exist without disrupting the physics we know. Dimensions aren't just mathematical abstractions. They're real, physical, measurable. We can test for extra dimensions in particle colliders. We can look for their effects in the behavior of gravity. We can use dimensional analysis to predict how systems scale. And we can use our understanding of dimensions to build models of reality that match what we observe. Feynman taught us how to think about dimensions, not by visualizing them all at once, which is impossible for higher dimensions, but by looking at slices, by understanding projections, by focusing on the properties that matter. He showed us that you don't need to see something to understand it. You just need to know how it behaves, how it affects the things you can measure. And that's the power of physics. Not just collecting facts, but building a framework for understanding. A way to take things you can't see, can't visualize, can't directly experience, and still make precise, testable predictions about them. Dimensions are the perfect example. You can't see 4 spatial dimensions, but you can calculate what would happen if they existed, and then you can look for those effects. And that's what science is. That's what Feynman dedicated his life to. Here's the deepest part. The universe is not required to make sense to your intuition. You evolved to navigate 3-dimensional space at human scales. Your brain is optimized for that. It's not optimized for understanding quantum mechanics or relativity or higher dimensions. Those things feel weird because they are weird, relative to everyday experience. But they're not weird relative to reality. They're just reality. And Feynman's gift was showing people how to accept that, how to let go of intuition when intuition fails, how to trust the math, how to follow the logic, how to test the predictions, and how to build a new kind of understanding, an understanding based not on what feels right, but on what actually is. So when you think about dimensions, remember this. You're not trying to visualize them the way you visualize a cube. You're trying to understand their properties, how they behave, what they allow, what they forbid. And once you understand that, once you grasp the logic, dimensions click. They make sense. Not in the way a picture makes sense, but in a deeper way, in the way that mathematics makes sense, in the way that structure and pattern and consistency make sense. That's what Feynman taught us. That's what makes dimensions click. Not visualizing 4-dimensional space, but understanding that 4 dimensions means 4 independent parameters, 4 degrees of freedom, 4 ways that reality can vary. And that understanding is more powerful than any visualization. Because it's true. It's accurate. It's how the universe actually works. We are creatures of 3 dimensions trying to understand a cosmos that might have more. And the fact that we can do this at all, the fact that we can build theories and make predictions and test them and refine them, that's extraordinary. We can't see the extra dimensions if they exist. We can't float outside space-time and look at its structure from the outside, but we can measure, we can calculate, we can deduce. And that's enough. That's Feynman's legacy, showing us that the human mind, limited as it is, can still grasp the fundamental structure of reality, that we can understand things beyond our direct perception, that dimensions, even extra dimensions, even higher dimensions, are not mysteries forever beyond reach. They're just another aspect of reality, another thing to measure, to study, to understand. So the next time someone asks you about dimensions, don't just say, up, down, left, right, forward, backward. Tell them what Feynman would tell them. Tell them that dimensions are freedom, that they're parameters, that they're the fabric of possibility itself, and that understanding them is understanding the shape of reality. Because that's the truth. That's what dimensions are. And once you see it, once it clicks the way Feynman made it click, you can never unsee it. The universe reveals itself not as a collection of objects in space, but as a geometric structure. A structure with dimensions, with curvature, with patterns. And we, tiny creatures on a tiny planet, have figured out how to read that structure, how to decode it, how to make it make sense. That's not just impressive, that's miraculous. And it's all thanks to people like Feynman who refused to accept, "I don't understand," as a final answer, who pushed and questioned and explored until dimensions clicked, until the pieces fit, until reality revealed its secrets. And now those secrets are yours. You know what dimensions really are. You know why they matter. You know how to think about them. That's Feynman's gift to you. Use it well. But wait, there's one more thing. One more piece that Feynman would want you to know, because understanding dimensions isn't just about abstract geometry. It's about understanding measurement itself, about understanding how we know anything at all about the structure of space. Here's the question: how do you measure a dimension? How do you prove that space has 3 dimensions and not 2 or 4? It seems obvious. You can move in 3 independent directions, so there must be 3 dimensions. But that's circular reasoning. How do you know those directions are truly independent? How do you know there aren't hidden dimensions you're missing? Feynman had an answer. You measure. You do experiments. You check if the laws of physics match what you'd expect for a given number of dimensions. Here's a simple test. Take a sound wave. In 3 dimensions, sound spreads out as a sphere. The intensity decreases as 1 over distance squared because the energy spreads over the surface of a sphere, and that surface area grows as distance squared. But in 2 dimensions, sound would spread as a circle. The intensity would decrease as 1 over distance, because the circumference of a circle grows linearly with radius. So you can measure how sound intensity decreases with distance. If it goes as 1 over distance squared, you're in 3 dimensions. If it goes as 1 over distance, you're in 2 dimensions. The dimension of space determines the behavior of waves. The same applies to light, to gravity, to any field that spreads through space. The way fields dilute with distance tells you the dimensionality of space. And we've measured this extensively. In every experiment we've ever done, fields behave exactly as they should in 3 spatial dimensions. The inverse square law holds. Space is 3-dimensional, at least on the scales we can measure. But here's the subtle part. These measurements only tell you about large dimensions, dimensions big enough that waves can spread through them. If there are tiny curled-up dimensions, dimensions smaller than the wavelength of light, then light can't probe them. They're invisible to this test. So we can confirm 3 large dimensions, but we can't rule out small extra dimensions. Not with this method. That's why physicists use particle colliders. Smash particles together at enormous energies. Give them enough energy to probe tiny distances. If there are extra dimensions, even small ones, high-energy particles can reach into them. And when they do, something strange happens. The particles gain extra momentum, extra energy states, resonances that shouldn't exist in 3 dimensions alone. No such resonances have been found yet. But the search continues. Each new experiment probes smaller distances, higher energies. And if extra dimensions exist, eventually we'll find them. Or we'll rule them out down to such small scales that they become irrelevant for physics. Either way, we learn something fundamental about reality. Feynman loved this aspect of science, the way theory and experiment work together. Theory predicts what extra dimensions would do. Experiment looks for those effects. And the conversation between theory and experiment drives progress. It's not about believing in extra dimensions or not believing. It's about testing, measuring, checking. And that's the scientific method. That's how we learn about dimensions. Not through pure thought, not through intuition, but through measurement, through observation, through checking our ideas against reality and letting reality have the final say. So here we are, at the end of this journey through dimensions. And what have we learned? We've learned that dimensions are more than directions. They're the structure of possibility itself, the framework within which reality exists. We've learned that 3 dimensions are special, but not necessarily unique. That extra dimensions might exist, curled up small, invisible, but real. We've learned how to think about dimensions we can't visualize, how to use slices and projections, how to work with abstract spaces and make them concrete through mathematics. We've learned that the laws of physics depend on dimensions, that forces scale differently, that structures behave differently, that everything changes when you change the dimensionality of space. And we've learned Feynman's greatest lesson. That understanding comes not from seeing, but from measuring, from testing, from building models and checking them against experiment, from following the logic wherever it leads, even if it leads somewhere strange, somewhere counterintuitive, somewhere your brain doesn't want to go. Because that's where the truth lives, in the places your intuition can't reach, in the structures your eyes can't see, in the geometry that underlies everything but reveals itself only through careful thought and precise measurement. Dimensions are there, in the fabric of space, in the laws of physics, in the behavior of every particle and wave and field. You just have to know how to look. And now you do. That's what Feynman gave us, the tools to look, the framework to understand, the confidence to explore, and the humility to let reality teach us, rather than insisting reality conform to our expectations. That's the shocking truth about dimensions. They're real, they're measurable, they're fundamental, and they're accessible. Not through mystical insight, not through visualizing the unvisualizable, but through physics, through mathematics, through the patient work of building theories and testing them. Feynman made dimensions click by showing us this path, by demonstrating that understanding doesn't require seeing. It requires thinking clearly, calculating carefully, testing rigorously, and accepting what the evidence shows, even when it's strange, especially when it's strange. So the next time you hear about dimensions, remember Feynman. Remember that dimensions are parameters, degrees of freedom, the shape of the space of possibilities, and remember that we can understand them, we can measure them, we can work with them, even when we can't see them. That's the power of physics. That's the beauty of Feynman's approach. And that's why dimensions click, not because they suddenly become intuitive, but because they become precise, testable, real. And once something is real, once you can measure it and calculate with it and make predictions about it, then you understand it. Even if you can't visualize it, even if it doesn't feel right. Understanding is not about feelings, it's about structure, about pattern, about the way things connect and relate and depend on each other. And dimensions are the ultimate example of structure, the framework within which everything else exists, the stage, except not really a stage because the stage is part of the play. The dimensions are part of reality, shaped by reality, shaping reality in turn. And we figured this out. Tiny humans on a tiny planet. We figured out the dimensional structure of the cosmos. Not completely, not finally, but enough to make predictions, enough to test them, enough to know we're on the right track. That's extraordinary. That's what Feynman celebrated, the power of the human mind to understand reality beyond direct perception. So take this understanding. Use it. Think about space not as a fixed background, but as a structure with dimensionality. Think about physics not as forces and particles, but as geometry and pattern. Think about reality not as what you can see, but as what you can measure and calculate and predict. That's Feynman's legacy. That's how dimensions click. And once they click for you, you see the universe differently. Not as a collection of stuff in space, but as a geometric structure, a pattern in space-time, a configuration in a high-dimensional space of possibilities. And you realize that understanding this structure, grasping this pattern, is what physics is all about. Welcome to Feynman's world, where dimensions make sense, where mathematics reveals reality, where measurement is the path to truth. It's a strange world, a counterintuitive world, but it's the real world. And now you have the tools to explore it.